breaking phones is really, really popular these days. People exploit the software in phones. They exploit the locks of phones. They unjail it. They do all kinds of things to the phone that a few years ago you would be doing to a computer, since the phone now is a computer. This talk is about none of this. This talk is about breaking a phone as a phone, not as a computer, and hence applies to even very old phones, the dumb phones or feature phones as they call them. We'll be discussing just how dumb the security features in the phones are. That little phone that also lives in every iPhone and every BlackBerry and every of the new smartphones. The phone that's used to make voice calls and send text messages. But that'll be the focus of this talk. And in the end, I hope to have enabled every single one of you to test the security of your own phone service. Since there's a lot of catching up work to do to bring phones up to the security they would deserve in this century. We'll be focusing on GSM, the world's most widely used communication technology. Supposedly it has 5 billion connections by now. These are not all phones, but I think most of them are phones. So it's fair to say that the majority of the world uses GSM on a daily basis. So chances are there's a lot of sensitive material being exchanged over GSM voice calls, acknowledging that even back when GSM was first designed, it was standardized, was a encryption function, in fact, several encryption functions by now, of which the very first one, A51, is still used today. Now that cipher was disclosed just a few years after GSM was standardized, way before GSM was popular at all, and shown insecure, at least by academic standards. It's not a strong encryption function such as AES, not even as strong as DES from back in the day. And that was already known 16 years ago. Now, ever since, academics have reminded every couple of years with a new paper of the insecurities of this A51 encryption function. However, all their breaks have not applied to GSM. They've broken the A51 cipher, but not the way it's used in GSM. So while academics had long written this off as a source for good papers, the rest of the world was really not affected at all. And after having heard that GSM is broken over and over again and nothing happened, people slowly started believing that, in fact, it was secure, since even as people that said they could break it, in fact, could not. And now, 16 years later, we can, and that's what this talk is about. We'll be talking about mostly two things. We're talking about this A51 encryption function and how to actually break it in a way that does apply to GSM. And then we'll picking up this challenge that the GSMA presented to us last year, where they reminded us of the fact that even if we can break an encryption function, that doesn't automatically mean that we can do anything to GSM data without the means to record the GSM data, to decode it, and to convert it into any usable format. And all of this will be added today. Before actually going into the security scheme of GSM, let me jump out of my PowerPoint here and show you some real data. This talk will be a little bit more hands-on than usually, with the goal of enabling all of you to work with GSM data, just as a few years ago you started working with, say, Wi-Fi data. Oops, if I do remember the password for this. Yes. So I'll be leaving out one step of this demonstration for practical as well as legal reasons. I'm not actually going to record any GSM data here. I did that back in my lab in Berlin from a real network but in a very defined environment where I knew I was only recording my own call. Now I brought this data, and we'll be working with this data now. If you want to record, again, only your own calls at home, the device you'll be needing is a USRP, or a similar software programmable radio. USRP interfaces nicely with the tool GNU Radio, and all you need to record chunks of GSM data is a single call that's already provided by GNU Radio. So let's assume we did all that and recorded this file of 71 megabyte of basically airwaves. Now there's a tool suite called AirProbe that's used to convert these airwaves into bits and bytes, and then even go a step further and decode the actual GSM packet. So let's run this AirProbe tool on that data we recorded. We'll have to give it one parameter that we also gave the USRP that tells it how many samples per second to take. And we'll have to specify which channel we want to decode. So in this case, we want to decode the time slot 0 and a beacon channel. And this, as it's scrolling down here, is GSM data already. You can immediately tell that it is by this filling pattern of 2B. It's very typical for GSM. Wherever nothing is sent, a 2B is put in its place. So these are the raw packets. Now those are not really readable yet, so let's present them in in another tool, in Wireshark. The current development version of Wireshark can already decode GSM packets. So we'll start a capture here on this interface. Actually filter this. And run the tool again. AirProbe automatically sends over all those packets as UDP to Wireshark now. And Wireshark, if I give it the right IP address, should be presenting all of this. It's the 141. So this is the GSM data that just flew by as hex numbers. As I said, this is a beacon channel, so it's the channel on which the cell broadcasts its existence. There's always traffic on this channel, even when the cell has nothing to say. It's a very periodic pattern consisting of, in this case, 6 or 8 paging requests, then the system information messages, again, paging requests, the system information messages. These system information messages contain information about the cell. So here's where the cell advertises itself. In the second one, for instance, it points to a list of other cells of the same provider that you could also be using if the signal is too weak from this cell. In the next one, it is advertising its location, its country, its service provider, and its actual cell number. Right? Well, location number. It's a collection of cells. Now, in between all of these, there's these paging requests. And they're usually empty, since they have to be sent periodically, but if nothing happens, there's no identity given. Sometimes something will happen. Let's see. So here, there's a TIMC that's being paged. So actually, something did happen in this packet, and the others are just empty. Now, this is the normal traffic you'll be seeing from any GSM cell as you're just listening to it. None of this is encrypted, of course. Now, if we sort this to find the interesting pieces of information, that'd be the immediate assignments. We'll get a step further. Immediate assignments are sent when something is actually supposed to happen, as in a voice call starts or text message is being sent. In this case, the immediate assignment consists of the command to please move to time slot 1 to receive control data on an SDCCH channel. That's another type of control channel. And it does have a reference, so the phone knows that it's meant to jump to this control channel. So this one phone will now hop to another time slot in that channel and start receiving control data there. Let me clear that here. Go back to our air probe. Start the same command again, but with a different parameter. So we said time slot 1 is a SDCCH now. I am outputting a little bit more data here. That'll be needed for the key cracking later. Let's just jump back to the Wireshark and see what's being sent on that control channel. This control channel has a few really empty frames. Well, one in this case. It again sends out a system information message, and it then immediately starts to encrypt everything. And of course, the air probe tool can't understand or parse anything beyond this point anymore. Right? This is where now the security kicks in. To jump ahead a little bit, let's assume we did know the secret key, right? Just to see what's happening on this control channel once it does start decrypting. Let's see. So I did crack these before, of course, and this is the secret key I got out of it. So if you pass this secret key as an added parameter to the air probe, it now decodes the encrypted packages, being all of these, following the first 4 that were not encrypted. Again, there's system information messages being sent periodically, basically as a beacon again. Since the phone is not listening to the main beacon channel anymore, it has to get this information somehow. There's a setup message that gives the caller ID of the person calling this phone. This is now being sent encrypted. And when I do my analysis, this is where I verify that, in fact, it was me calling my phone. So I can safely decrypt the rest and not interfere with anybody else's data. And then the only other interesting piece of information in here is yet another assignment command where it tells the phone to move to yet another channel for a traffic channel. This is where the actual call then happens. So it jumps twice, right? And so to not jump ahead any further, let's keep it at this. We'll look at more data a little later. Now here's the way that the security is supposed to work, or does work, just not too strongly in GSM. The phone SIM card shares a secret master key with its home network, and only with the backend servers in this home network. This key is very relevant for billing purposes, of course, to authenticate the users. So the operators try to keep these keys as locked down as possible. They don't share it, for instance, with the base station that the phone is currently communicating with. The base station instead gets a session key assigned from the home server of the phone. That session key is derived from the master key using a random number. So the base station gets the random number and the session key, sends the random number onto the phone. The phone, who also has the master key, derives the same session key, and then the base station and the phone can communicate using A51 in this case. And that's exactly the encryption function we want to